Fucking A. Okay, guys, sorry, I'm here. If anybody's in chat. Let's see. Oh, thanks. Yeah, I should do a mic check. So great. How's the sound? Is it too noisy? Well, okay. So we're going to be reviewing the chapter 14 material and 13 material. So your partial differential equations and your complex value functions and residue theorems, integral theorems, and so on. And since, Russell, since you're the only one here, if you have any requests, go ahead and reference a section or a problem in the book, or just give me a broad topic. I'm sure I have some problems over here I can come up with, or you can give me a specific problem. Okay. If not, we can go ahead and start going over some partial differential equations. Chapter 13, all right. Good idea. Okay, so for chapter 13, we have several types of differential equations. So we have the problem, let me change the color. So we have the problem where we have a plate. And it could be a finite plate or an infinite plate. And we're interested in finding a temperature, a steady state temperature, right? So this is steady state temperature means that we only have temperature as a function of position. So this is the temperature that we eventually we will have in the long run. And so the differential equation which governs steady state temperature is Laplace's equation. So that's where the derivatives, second derivatives of the temperature function are 0. Okay. So since we have just a two-dimensional problem, we have just position x and y, this amounts to saying the partial derivatives, the second partial derivative of t with respect to x twice, plus the second derivative with respect to y twice, must be 0. Okay. And we're also going to have some initial conditions. So, well, we're going to have, let's say, 4 boundary conditions, right? And I'll use specific numbers. Let's make this 5 centimeters. Let's make this 7 centimeters. Okay. And then we're going to have boundary conditions. So we have 4 boundaries. Okay. And for each boundary, we're going to write down a condition. Now, the simplest case is where 3 of the sides are 0 degrees. Okay. And the 4th side is in general some function of x, right? So let's label these correctly. So the left side is the temperature when x is 0 at y, for y between 0 and 7 in this example. This is the temperature at position x when y is 7 for all x's between 0 and 10. Right, and this is the temperature at the right side. So at when x is 5 centimeters for y's between 0 and 7. Okay, so the fourth side in general is going to be some function of x, right? This is the temperature at position x when y is 0. Okay. All right. So we want to come up with some temperature that can have a constant. For simplicity's sake, a constant would be nice. If we have something like x, that works as well. Okay. So the key here, of course, is to use separation of variables. Yeah. So separation of variables tells us that we can assume that the temperature function can be separated into a function of x and then a function of y. Yeah, a product of a function of x and y. So that assumption is that this can be broken down in just a function of x. We'll call it big X and big Y. Okay. All right. And then if you plug that into the Laplace's equation, right, then when you have the partial of t with respect to x twice, you're just differentiating the x factor. Right? So that'll be x differentiated twice with respect to x. And then this is just a function of y, so we left it alone. Plus the derivative of temperature with respect to the y coordinate twice. So again, we leave this alone. Oops, let me erase that. Alright. And so Laplace's equation says that at steady state this derivative should be 0. Alright, so now here's the trick. We bring all the x's to one. We just separate the variables on either side of the equation. So we're going to get this. You can do the quick algebra to see that. And the argument is that this over here is just a function of x. And this is just a function of y, right? So it's not possible that if one side changes, the other one is constant, right? So if this side changes with x, this couldn't, because this is just a function of y. So it must be true that this is equal to some constant. And we let that constant just be minus k squared for convenient reasons, for convenience. Okay. From here we get two separate equations, and these are now simple first order differential equations. The first one we get x double prime, where we now know that double prime means derivative with respect to x twice is minus k squared, and the second equation is negative y double prime, second derivative with respect to y over y equals minus k squared. Okay. Alright, so we solve both differential equations. I'll write it like so. It's just some algebra there. And we can see that solutions to this equation, I'll use your book's notation. The second order differential equation is going to have two independent solutions, and clearly it's going to be a sine and a cosine. Right, you can easily check that the that sine of kx will satisfy this differential equation, and so will cosine of kx. Okay. That's your book's notation. And then if I write this, I'll get y prime plus k squared times y 0. Just rearranging that. And here we can have, we see that the, again, second order differential equation, we're going to have two independent solutions in our fundamental solution set. And now here we can clearly see that this is a solution. Again, just differentiate this twice and plug it into the equation, it works. All right. But it turns out that you can, because of the way hyperbolic sine and cosine are defined in terms of exponentials, you can also see that hyperbolic sine of ky is a solution. And so is hyperbolic cosine, so sinh and cosh. Right. All right. But which ones do we choose? Well, actually, let me say something more. Not only are these solutions, but so are these. So, and we'll see why we're going to do this. So sinh of k, then 7 minus y. And cosh of k times 7 minus y. Now, why would I want to do this? Well, to understand why we're doing this, you want to go back to the boundary condition on the top of our plate. Okay. We want the temperature when y is 7 to be 0, right? Okay. So let's come back here and just write that. Let's just see. So notice that when y is 7, right, when y is 7, we're going to get sinh of k 7 minus 7, right? So sinh of 0, we all know is 0. So what we're doing is we're just choosing a convenient way of writing our fundamental solutions to this differential equation so that our boundary condition is satisfied. Now, cosh of 0 is 1, so that won't work, but we'll throw this cosh out. All right. So let's just, right. If you had an infinite plate, by the way, this would work, right? For infinite plate. So if y went off to infinity, it's because this exponential, when y gets large, vanishes, right? It goes to 0 as y goes to infinity. So that would satisfy that third condition. All right. So now what we do is we consider. So we consider t, right? So t of xy is x times the y function. So we can bring that together, and we can write this. We're going to have. I'll write the y stuff first. Sinh k 7 minus y times some combination of sine and cosine plus cosh, and this cosh part is kind of unnecessary. You'll see that it'll go away, but and some combination of sine and cosine. All right. So now what we need to do is, of course, so this is a general solution. It has, if you multiply everything in this set with everything in this set, you're going to get 4 terms. So you're going to end up with 4 arbitrary coefficients in your general solution, A, B, C, and D. We need to determine what these coefficients are. And the boundary conditions will tell us what those are. We're going to successively consider the boundaries in order to eliminate some of these coefficients, figure out what they have to be. Okay. So let's see. Let's start with the leftmost boundary, right? Okay. So the leftmost boundary is going to be when x is 0, temperature has to be 0. So I'll write that. Right, for all our y's. All right. So let's see. see, now if you replace x with 0 in all these, you're going to get sinh. Maybe I should have started at the top side, I don't know. Of course, when x is 0, we get sine of 0, which is 0. We get cosine of 0, which is 1, sorry. And plus cosh. Yeah, I should have started with the top side just to get rid of this cosh term. So I'll do that. Alright. Okay. Let's look at the top side. So what was the top side? Okay, so when y is 7, our temperature must be 0. So we get sinh of 0, which is 0, which makes all this stuff irrelevant because we're multiplying by 0. Plus, let's see. Okay. Then we get, when y is 7, we get cosh of 0 is 1. And then we get c cosine 0. Alright, and that must be 0, so that tells me d is 0. Right, and 1 second. Okay. So let's see. I lost my train of thought here. So this tells us d must be 0. Okay. Oh yeah, and if you look at the so if you look at the corner here, let's just think of it that way. I guess, what would that mean? So that's when x is 5. Y is 7. So what you would get is again, sinh of 0, 0, you get 1. I'm trying to reason why this has to go to 0. Oh, okay. You know what? I'm sorry, right there. This is it. Okay. Alright. So if you come back here, we essentially have b times sinh. I completely this was all I needed. D cosh. Okay, so we know that sinh and cosh are linearly independent, right? And so if that's 0, that means that both b and d are 0. Alright, so by definition of independence. Okay, and then using this condition, we see that c must be 0, because if d is 0 from over here, then c must be 0. So all this stuff just goes away. So I apologize. Alright. So let's update our function. So we just have the sinh left, right? The cosine didn't work out. I mean, the cosh didn't work out. And notice that we've already decided that b must be 0. Okay, so there we go. So we used the left boundary, the top boundary. Now we're going to use the right boundary. And that's not going to determine what A is. It's going to determine actually what K is. So the right boundary, we have that X is 5 and Y is something between 0 and 7. So using the right boundary, X is 5. So you get cinch. Right? And you get A sine of 5K. Okay. And this has to be true for Y's between 0 and 7. Okay, so the argument is that if this must be 0 for all Y's, and this is a function of Y with changes, it's not always 0, right? And we don't want A to be 0 because then you get a trivial solution and even the boundary condition wouldn't work. It's this factor that must be 0. It's the sine of 5K that must be 0 for this right boundary to be satisfied. So, okay, then we set sine of 5K equal to 0. And we say that, okay, sine is 0 when its argument, namely 5K, is some multiple of pi. Yeah, sine of any multiple of pi is 0. Which gives us a formula for K. And if you've done this for homework and stuff, I'm sure this looks familiar. It's of that form, n pi over L, right? Alright, so okay, now let's come back and update our function again. So now we have temperature at xy is cinch, and now we know what K is. It's n pi over 5, 7 minus y. We have a coefficient A, and then we have sine of 5K. I'm sorry, KX. I just came back here and replaced K with what we know what it is, right? Okay. All right, and notice that this is a solution to our differential equation, which satisfies 3 of the boundary conditions, regardless of what integer n is. N is some integer, right? So we can subscript. So we have infinitely many solutions, right? For each integer n, we have a solution. Each positive integer n. And since we're dealing with a linear differential equation, you can use superposition to add up all these solutions over all n's. Well, do I have to include n equals 0? Like, what happens when n is 0? Well, when n is 0, we have a sine of 0, so that's 0. So that's just 0, so not interesting. So we're going to say that our temperature at position xy now is the sum over all positive integers of these guys. Yeah, superposition here. Alright. So, okay, so we've used 3 of the boundary conditions. Now we're going to use the 4th bottom one. And what that's going to help us do is figure out what these coefficients are, right? And so we want to recall the formula for those coefficients without too much explanation. It has to do with Fourier series. But I'll just give them to you, the formula here. Okay, so let's look at the bottommost boundary. Okay, so the bottommost boundary was a function of x when y is 0 there. And for this problem, we define this to be x. Okay. Just for this problem. And the formula for these coefficients is, it's 2 over L. So this is really related to finding the Fourier coefficients for sine when f is an odd function. But I won't get into the details. You can see how that's related. Yeah, f of x, and then sine n pi over L. Right, so you kind of need to know that formula, right? Alright. So for our particular problem, L happens to be 5. And our function is x. And so there we go. And yeah, you know, if it's a constant, then it's a lot easier because of the integral, but this is not bad, right? It's an integration by parts. Integration by parts, where u is our polynomial x, so the du is just dx. dv is our differential sine n pi 5x dx. And integrating that sine, we all know that we get 5 over n pi negative cosine. Just some basic integration there. Alright. So this is just, you know, plug and play. So let's see. U times V parts. Let me just write that down in case for some reason you're just not that familiar with it. So you have U times V. Minus, as part of the formula, the integral of v du, but v has a negative coefficient. I'll just pull that out to get a plus, and then the cosine times dx. Okay, and of course this is a definite integral, so I'm going to go ahead and include the bounds here. Alright, so let's go ahead and evaluate this term at the upper and lower bounds. So you get when x is 5 at the upper bound, you get negative 25 cosine of n pi. And at the lower bound, x is 0, right? X is 0, and then we have an x as a factor, so the whole thing will be 0 at the lower bound. Okay. Alright, and here we're integrating cosine, so we get sine. I guess I could, okay, I'm multiplying the whole thing by 2/5. Scroll up. I know, terrible handwriting. Just erase that. Alright, so let's see. Oh yeah, just, gosh. So here we got an x, and the argument is sine. And at the upper bound, when x is 5, we get sine of n pi, and again, sine of any integer multiple of pi is 0. And at the lower bound, we get sine of 0. So this whole term just goes away. 0 at both bounds. So there you go, we get negative 50. I'm sorry. Negative 10 cosine n pi over n pi. And of course, this is is that? Oh, yeah. Okay, if n is even, then we get a cosine of an even multiple of pi, so that's 1. And if n is odd, and again, I'm choosing a pretty simple example, right? It's not like we have 4 different cases here or anything. So this would be positive 10. Cool. All right, so now we have our formula for the coefficients. Oh wow, so let's see, now that we have that, we have our function. Right, let me just copy this real quick. My computer isn't liking all this. Jeez. Okay. Alright, so now we have our function, and actually we're done then, right? So the only thing you want to do is, I guess, complicate matters. Sorry, my computer's lagging. Oh, come on. Let me do this to me now. Oh, I can't write with the mouse. There you go. Alright, so we have a nice formula, and we are done. This is clearly going to be alternating. We're going to have negative 1 to the n plus 1, because when n is even, we get a negative. So, and when n is odd, you get a positive. And that's it. Alright. So, do we maybe want to see a like a heat problem where time is involved, where we don't have a steady state? Well, we do, but we're interested in the temperature of something along a rod at, say, position X, and at a certain time. So that's the diffusion or heat equation. We should cover that. Cinch. I'll do that next if that's okay. Yeah, alright, cool. Thanks. And we'll change it up because it's interesting, because you have like, for the diffusion equation, you have like an initial steady state and you have a final steady state, and we'd like to know how to deal with that. So we'll go over that. I'll go ahead and create a problem then. I can also go over the problem in your book, so you tell me if you'd rather do. I think one of your classmates brought the problem that was problem number. I think it was just the example. We'll change the numbers, that's what we'll do. Cool. Okay. Alright, so for the heat equation, what we're doing is we have to, I think of it as like a rod of a certain length, right? And it has, the length of the rod is given by, the position along the rod is given by coordinate x. And it has a certain length. And we would like to know the temperature of this rod at each position, but at different times. So this time we don't have just a function of coordinates x and y position, we have a function of position x and time t. Okay. And we would model this. The temperature distribution here would be the heat equation. Yeah. All right. So this would be. Maybe I'll use U because your book uses U, so I won't throw you off. Okay, I'll use U. All right. So then we have the heat equation. Okay. So the second derivative of U should be equal to 1 over some constant alpha squared. The derivative of U with respect to time. Right. Okay. So we're going to set up the differential equations and then look at the boundary conditions, right? So again, we assume separable differential equation. So your book splits this up into a function of just position, so they call that big F, and then times a function of time, which they call big T. Okay. And using this, we get a nice equation where we differentiate U. So since we only have one spatial coordinate, x, right? The left-hand side in the heat equation just means second derivative of U with respect to x. There's just one space coordinate. Right, the del operator there has to do with the derivatives with respect to the spatial coordinates, not time. Okay. So when we differentiate U with respect to x twice, we're just differentiating the factor that has the x's, right? So this would be fxx times t, and that would have to be equal to 1 over alpha squared partial U with respect to t, so we just differentiate the function of t. I don't need that. Alright. Times f. Oh yeah, I forgot the f. And so you follow the same trick where you bring all the f's to one side. So fxx over f. And that's equal to 1 over alpha squared, and you bring the temperature stuff to the right-hand side. And the same argument is that this must be constant, because it's not possible that one is changing with x, but the other cannot, right? Because this doesn't have an x. So this must be constant, and they set it equal to the constant minus k squared. Again, so that's exactly the same thing we did with the Laplace's equation for the steady state problem. All right. So that gives us two differential equations, right? We have fxx plus k squared times f is 0. And then we get derivative of t with respect to time plus k squared alpha squared t is 0. Right? Just by setting this equal to this to get the first equation and setting that equal to that to get the second equation. All right. And then we can just see what the solutions must be, right, to the second differential equation. This looks really familiar. It's exactly the sine and cosine we had before. So f is either sine or cosine. Remember, f is a function of x. Now, for the differential equation involving the time factor, notice it's a first order differential equation, right? It's not second order. So we're just going to have one solution, one fundamental solution here. So, and you can confirm very quickly that this solution, a solution here is that. Right. So just differentiate once, plug it into the differential equation, it is satisfied. So then the general solution for the heat problem here, would be this exponential times some combination of the sine and cosine. Alright. Alright, so how do we determine what these coefficients A, B, and K are? Well, we have to look at the conditions, right? The boundary conditions, the initial conditions, the final conditions. So now we're going to draw a picture where it's going to look like a plate problem, except only one axis represents position. The other axis represents time, right? So when we look at the temperature at time 0, we're kind of looking over here. And as time goes on, we have different distributions for temperature. Okay. So now let's do this. Let's make this, let's say, 0 to, let's make it 5 again, why not? Alright. Okay, so now how are the conditions going to be given? The conditions are going to be given in terms like, we want at position 0 for all time after the initial time. We want the temperature to be something, let's say 20 degrees, right? And then the right side of this rod for all time past the initial time. The rod will be held at temperature, and let's make it not 20 because that'll be not that one. Let's make it, let's say 5. Okay, let's make it 10 degrees. No, 30 degrees. Make it positive. Alright. Okay. And then let's see. This is going to be the temperature distribution along the rod at time 0, right? So that's called the initial condition. I guess technically these are boundary conditions for the rod, left endpoint, right endpoint. This is the initial condition for the rod, as in what is the distribution of the temperature at time 0. So this is going to be some function of x, right? So suppose at time 0, the left temperature, the temperature at the left endpoint is 0, but at the right endpoint, it's whatever, say 40 degrees, like who cares? Right. So the question is, if initially the temperature at the left endpoint is 0 and the right endpoint is 40 degrees, what would the steady state temperature be initially, right? So since we would have a steady state at time 0, we know the Laplace's equation is satisfied for this function. Echo? Boy. Well, I don't know if the speaker's on. Hey, Thomas. I'm going to put it in my earphones just to see what you're hearing. But yeah, the Laplace's equation is satisfied. So since f is just a position of one spatial variable, this means that the second derivative of f with respect to x is 0. Earbuds. Okay, let me just see what you're hearing. just turn the mic down. Let me just turn the mic down. Yeah, I definitely hear an echo. Let me just turn the mic down. Yeah, I definitely hear an echo. Don't go away. One second. I'm gonna stop the stream. One second. I'm gonna stop the stream. Okay. Is it still there? Okay. Is it still there? Hello. Cool. Now, alright. Now I just go there. Change my camera because it's all freaky. What is it doing? Cool. Now, alright. Now I just go there. Change my camera. Hey, it's all freaky. It's all zoomed in. What is it doing? We don't need it. Cool. Now, alright. Now I just go there. Change my camera. Hey, it's all freaky. Alright, it's all zoomed in. What is it doing? We don't need it. Cool. Now, alright. Now I just go there. Change my camera. Hey, it's all freaky. Alright, it's all zoomed in. What is it doing? We don't need it. Cool. Now, alright. Now I just go there. Change my camera. Alright, let's get back down to business. Alright, it's all zoomed in. What is it doing? We don't need it. Alright, let's get back down to business. Alright, it's all what is it doing? We don't need it. Cool. So, let's see. Alright, anyway, sorry, the initial condition. Here we have the temperature 0 at the right endpoint, 40 degrees at the right endpoint. Left and right, sorry. So, and we want to look for the steady state. So we differentiate, so Laplace's equation is satisfied initially. And if we differentiate once, and differentiate twice, so integrating once, we get a constant. Integrating another time, we see that our function, our initial steady state, must be a linear function. Okay, and of course we want to choose A and B so that we get the correct temperatures at the two endpoints. So when x is 0, we need the temperature to be 0. And when x is 5 at the right endpoint, we need the temperature to be 40. So A equals 8. A equals 8. Alright, so we have what we call the initial steady state, right? It is 8x for x is between 0 and 5. Alright. And we'll call that UI, because your book, I think, uses UI. That's the initial steady state from 0 to 5. Alright. So we also need to determine what we call the final steady state. That is to say, after we start the stopwatch and time goes on, we're now holding the left endpoint of the rod at 20 degrees and the right endpoint at 30 degrees. And eventually, in the long run, as t goes to infinity, we're going to get a steady state, right? So what would that be? So now we're finding the final steady state. All right, so the final steady state, remember that we're going to hold the left endpoint of the rod at 20 degrees. This is for time greater than 0. And the right endpoint, what was it? 30 degrees. All right. And so now we're going to have a steady, and so now as t goes to infinity, okay, let's see. Notice as t goes to infinity, this will just go away, right? And we're going to end up with a steady state distribution. It's going to be just a function of x. So I'll call that U sub f for final temperature, steady state temperature. And again, it's going to be linear for exactly the same reasons that we had before. Steady state, Laplace's equation is satisfied. So we just integrate twice to get some linear function of x. All right. Oops. So sorry. Yeah, that should be 0. We integrate twice to get this. And then at the left endpoint where x is 0, we need the temperature to be 20. So b is 20. And at the right endpoint where x is 5 centimeters, whatever units you're using, the temperature has to be 30 degrees. So clearly A must be 2. Okay, so now we have the final steady state. AX plus B is 2x plus 20. Alright. We have final steady state, we have initial steady state. So how do we deal with these states? Well, the secret is to do the following, right? You're going to find a solution to the homogeneous problem, so to speak. So this is where we assume the temperatures are 0 degrees, 0 degrees. At infinity, the temperature has to go to 0 degrees. So we're going to find solutions to this problem. Okay, and so we know that in that case, let's see, what would happen? Okay, we would have these differential equations. We have their solutions. And we would get something like this, right? So we get these solutions. And what we're going to do now is use these homogeneous boundary conditions to find A, B, and K, I believe. So we have e to the negative k squared alpha squared t, and some combination of sine and cosine. So A plus B. Okay, so this is should be routine at some point, like on the left boundary x is 0, right? So when x is 0 for all time, sine of 0 is 0, cosine of 0 is 1. This has to be 0. So now notice we are solving the homogeneous equation, right, where the boundary conditions are all 0, right? We're ignoring the fact that we want the left endpoint to be 20 degrees, the right endpoint to be held at 30 degrees. So of course B has to be 0. All right. Now the this boundary condition at t infinity is already satisfied, right? Because as t goes to infinity, this exponential goes to 0. So now let's look at the right side. Okay, so that says when x is 5 for all time, we need this to be 0. Alright. Of course, for this to happen to non-trivially, a cannot be 0, so sine must be 0. Meaning that its argument must be a multiple of pi. And there you go, we've solved for k. Cool. Alright, so let's see what we have. So now we have u of xt is e to the negative k. I just figured out k, 1 second. Oops. Alright, so we have u of xt is this exponential e to the negative alpha k squared alpha squared t, and then we have a sine kx. Right. So this is a solution to the homogeneous, where the boundaries are 0 degrees, and this can be indexed with an n, because this is a solution for any integer n. So then we would get a solution by superposition by adding this over all positive integers. We have our coefficients a sub n. This is our decaying exponential, not complex. Whoa, okay, that video is all wrong. Okay. Okay, again, this is not our solution because our boundary conditions are not, right, that we've simplified the boundary conditions. Okay, so how do we involve the original boundary conditions where this side is 20 degrees, this side is 30 degrees? Well, here's the trick that your book kind of hints at, doesn't explain very well. No disrespect to Boas. What we're going to do is we're going to include this part, and then we're just going to add the final distribution. Okay, let's see why this works. Okay, let's see why this works. So if we take the solution to where the boundaries are all 0 and then you simply add in the final steady state, why will this work? Well, let's see. Alright, so at the left endpoint, right? So when x is 0 at time t, okay, we get sine of 0. You agree that when x is 0, this will be 0 here. So sine of 0 is 0, so everything in the sum just goes away, and you're left with the final steady state. So that works, right? So the steady state at at position 0. And what was that? Let's see. 2x plus 20. Right, so the final steady state is 2x plus 20. But when x is 0, this just gives me 20 degrees, which is the correct left boundary condition that we started with, right? 20 degrees. All right. And so what about the right endpoint? Well, when x is 5 at time t, okay, once again, because x is 5, right, the 5's cancel, you get sine of a integer multiple of pi, which is 0, so again, everything in this sum just goes away, it goes to 0. And you're left with the just the final steady state. At position 5, when x is 5. Alright, so that would be, according to our formula, 2 times 5 plus 20. So that's 30 degrees. And that again checks, right? It is the 30 degrees that we wanted originally. Alright. Okay, now what about the initial condition? So let's recall the initial condition was that at time 0 we have an initial steady state, and this was given by the function 8x, which we derived above. Okay, so let's see. Let me just copy this down. Plop. Uh-oh, I ran out of paper. Oh, jeez. Oh, it's never mind. Alright. So let's see if this works, right? Okay. So when time is 0, what are you left with? I think I can extend this. Let me just do this really quickly. Sorry, I'm going to do some copying and pasting. Alright, cool. I'll just get rid of this scrap. Okay. So, alright. So, so now we're looking at the fact that at time 0, this needs to be the initial steady state, namely 8x, right? Okay, so t is 0, which we get the exponential function at 0 is 1, so that just takes those out. Sine of plus final steady state. Okay, so what we have is the equation this is initial steady state on the left, and that's equal to this sum plus the final steady state. So now, to satisfy this condition, right, we need to choose our a's appropriately, our coefficients in this sum. So I'll just bring the final steady state to the right by subtracting, and then what we have is a series being equal to some function of we can assume periodic function of x. And so we know exactly how to find these coefficients for these problems, right? A sub n can be 2 over the period, or yeah, half period, whatever. One integral from 0 to L. And here the function that we're expanding in this to this sine series is the initial steady state minus the final steady state. So you can think of this as a formula once you know what your initial and final steady states are. So here's a formulaic way of finding these A's. Okay, so in our case, L is 5. We have the integral from 0 to 5. And let's see, we had the initial steady state we figured out was 8x. The final steady state we figured out is 2x plus... Does anybody remember? Crap. 30 degrees, right? So at 5 plus 10. There you go. Okay. I hope that's right. I erased it so I forget exactly what it is. Alright, and then you would have to do this integration to figure out the coefficients. Yeah. I'm not going to do it. I just wanted to review the I guess more complicated procedure for when you have an initial steady state in a bar and a final steady state, right? So what we did is we first solved the easier problem where all these boundaries were 0, including the one at infinity here. Okay, and that way we got a solution. It's a series with these arbitrary coefficients. We found a k. K was like n pi over L formulaically. Okay, and then what we did is we found an initial steady state, a final steady state, and we said that our solution can be written as this solution to where we have the boundaries being at 0 degrees. This is just a outline of what happened here. Plus the final steady state, right? Okay, and then to solve for the coefficients, we use the fact that initially, well, of course that's code for time 0, we had initial steady state must be equal to final. Must be equal to this right hand side. So this gave us a way of solving for these coefficients so that we can satisfy this initial condition. And so we had initial minus final equals this series. And then we used our formula for the coefficients. Alright, that was just a quick outline of what happened. Right. Alright. Alright, what else would you like to see besides this? I'll take requests, like if you have section reference numbers or problems. I have a book here, I can look them up. how did you get the final steady state? Okay, let's do another example of how to find steady state. Okay, so I'll try to draw. Oh my goodness, I forgot. I forgot this last time, but I have shapes. All right, there we go. That's prettier. This is time. This is position. I just made it ugly. Okay. So let's pick a temperature here, right? So we want the left endpoint of this rod, so that's when x is 0. Let's make this, let's say, 100 centimeters long. Let's say we want this to be 50 degrees, right? The left endpoint is being held at 50 degrees. And suppose that the right endpoint, that's when x is 100 for all time after initial time. Suppose we want that to be 0 degrees. Okay. So what happens is that in the long run, for large values of t, right, as t goes to infinity, the bar should achieve a steady state. Okay. So what we have is the final distribution of temperature as just a function of x, because t went away. We didn't care about it. It's a steady state. And the question is, how do we come up with this formula? Well, since this is steady state, you have to recall that Laplace's equation is satisfied. So we only have one spatial variable, that's x, so this amounts to the second derivative of uf with respect to x. And to recover what uf is, we just integrate once to get rid of the first, the first derivative with respect to x, and we get a constant of integration. And then we integrate both sides again with respect to x, and we see that our final steady state is ax plus b, because we're finding antiderivatives, right? And then you use the boundary conditions to find a and b for your final steady state. So, right. Let me come over here. All right, there you go. So we found the form of the final steady state as a function of x, I should say. And we know that when x is 0, the left endpoint of our rod is 50 degrees. Oops, I'm going off screen. My bad. Right. So it looks like we found that the b has to be 50. And then at the left endpoint of our rod, the temperature is 0. So when x is 100, right? It's a 100 centimeter rod or something. The temperature is 0, so then we get a times 100 plus b must be 0. So a is negative 1/2. Now, we could make it more complicated, obviously. What if the... could we make it more complicated? Yeah, I suppose, but I don't know enough about these to try to complicate matters here. So, does that make sense? You just look at the what we were holding the left endpoint when x is 0 of the rod or whatever, what temperature that is, and what we're holding the right end at. And then we're looking for steady state, so that means that time's not a factor because this is in the long run. And if you have steady state, Laplace's equation is satisfied, we integrate twice to get a form for the final steady state. And then use the boundary conditions to actually find these coefficients. Okay. All right, so any other requests? Oh, wait a minute. Okay, I need to check chat here. All right. All right, any other requests? Or we can do some complex stuff like residue stuff. All right, yeah, we have 35 minutes. Showing beta. All right. Okay, string vibrations, wave. Okay, wave equation, so. Let's look at a problem then. Same idea, right? Except it's a different variation on our differential equations. Oh crap, cancel. Alright. So this type of problem kind of reminds me of the rod, right? Because you have two ends, and you string a string. You have a string, right? And you have a vibrating string. So you have a string of a certain length, and the horizontal displacement along the length is x, and this will be y, right? Y being like the vertical displacement of the string when it's vibrating, right? So you get some sort of vibrating string, and so y represents the height from equilibrium. Whatever. Okay. And so so at a position x, at a certain time t, our string will be displaced vertically, y. So we have y, the vertical displacement of the string, is a function of x and t. So apparently, what governs the behavior of this vibrating string is the wave equation here. Well, it governs it, but models it, I should say. So the second derivative of y with respect to x should be equal to 1 over some constant, so that's speed squared, right? Then the second derivative of y with respect to time. So we have second derivatives on both sides. Right, to solve this differential equation, what do? As before, we simply assume separation of variables, so we'll see what your book calls these x and t. Okay, so we can factor this into a function of just x and a function of just t. Okay. And then we see that if we plug this into the wave equation, we're going to get y, yxx equals 1 over v squared ytt. But then y is factored into a function of x times a function of time. And likewise, you have x times t differentiated with respect to time twice. Alright, so that, let me go through this business. separate the variables. We make the argument that this must be constant. And what are we going to call the constant? Minus k squared again. Why not? What did you say, Thomas, there? All in favor may be represented by me, your local corrupt senator. Oh, okay, good. All right. All right, so this gives us the differential equation, the second derivative of x with respect to x plus k squared x is 0. And that should look familiar. We should know the solutions to that by now. And then this. I'll use prime because now it's understood that it's a derivative with respect to time. Well, look, they're exactly the same form of a differential equation, right? Except this is the independent variable is x. Here, the independent variable is time. So, geez, I wonder what the fundamental solution sets are. Well, here's a sine and a cosine. I forgot a v, didn't I? Yeah, that's okay. There's a v squared here. So here it would be similar, except now we have a function of t. So we get sine of kvx. And cosine kvx. Oh, brother. Alright, so what's going to happen is that we're going to have for our general solution, what do we have? Y of xt is some combination of these guys. I should decide how to write this. All right. I guess we need an initial condition, right? So let's just do a problem here. One second. String L. Is there a problem in the book that was worthwhile, Thomas? Do you know? For section 4. I guess we can just do problem 5, I guess. All right. Cool. So I'll just do problem 5 from section, unless you come up with something better, Thomas, but chapter 13, section 4. Yay! Okay. Number 5. Alright. So let's look at it. I just needed some kind of initial conditions. I don't want to make anything up. So we have a string of length L. it's initially stretched straight, and its ends are fixed at the ends for all time. That gives you boundary conditions, right? So what they're saying is that the displacement of the string at the left endpoint for all time must be 0. It's fixed. And likewise, at the right endpoint, the displacement vertically at the right endpoint for all time must be 0. It also says the string of length L is initially stretched straight. I'm assuming that means that initially, i.e. at time 0, the displacement is 0, but I'll double check on that. But, I see. But the points initially are given velocity. So they give you another initial condition, interestingly enough. And what's that initial condition? They're saying that the derivative of y with respect to t, so the velocity in the vertical direction, at time 0 is as indicated in the diagram. Okay, so what does the diagram indicate? They drew this picture, not to be confused with the picture we're drawing above, where y is the vertical displacement of string, but they give you initial velocity as a function of x. And they drew a triangle like so. Okay, so this is the midpoint of the string. This is some height. They're calling this h. Right. And this represents initial velocity. So you have to be careful. You just to see remember what this means. It means the derivative of y with respect to t. And we're gonna then write this function. This is initial velocity. And it's a piecewise function, clearly. So we have a positive sloping line for the first piece for x between 0 and half of the length of the string. And what's the slope of that line? H divided by L over 2, so 2h over L. Okay. X with intercept 0. And then for x's between after the second half of the string, right? It's a negative sloping thing. And then we have, let's just see really quick. I'm kind of slow here. 2h, okay. Yep, that works. Cool. Alright, so is this enough? So notice that we have two boundary conditions. So that's for when x is 0 and L. They're pretty simple. And then we have two initial conditions, right? It's because we were involving second derivative of y with respect to time. So we needed two conditions for this. Okay. So we still have like 4 conditions, 2 initial conditions, 2 boundary conditions. That should help us out determining coefficients, right? Okay. So what did we decide our solution is? Well, we said it's some linear or some combination of, multiples of these. So there's 4 different terms. You have a sine term, you have a cosine term. So it's sine kVt. I don't know the best way to write this. And you have a cosine kVt in there. So then we start using our initial and boundary conditions to figure out the coefficients, right? But I kind of need that. And never mind. All right, so let's use the left boundary. Okay, so that says that at position 0 for all time, the end is fixed. So this vertical displacement is 0. All right. So when x is 0, we're just left with a. And over here, we're just left with a c. Okay. So what does this say? This says, okay. So we have a linear combination where the coefficients are a and c. A linear combination of two linearly independent functions. Therefore, a and c have to be 0. Okay, that's from the left boundary. Let's update our function. So we get sine plus and then what are we left with here? D. Alright, but now we can use, I believe, what do you want to use here? Do you want to solve for k now, or do you want to use initial conditions? So let's start using initial conditions, right? So at time 0. So what do we know at time 0 about the displacement of the string? Well, the string was initially stretched straight, meaning its vertical is flat, right? Its vertical displacement is all 0 at time 0. So replacing t with 0, we get sine of 0 is 0. Cosine of 0 is 1. Right? So if that must be 0, d has to be 0, right? Because x is changing with, sine of kx is changing with position x. So d has to be 0. Okay. All right. So let's update our function. D is 0, so we're just left with the sine terms, I guess. It's all sine from here on. All right. Cool. So what did we use so far? Oh yeah. So now we're going to use the right boundary. Right. We use the left boundary. Then we use the initial condition for displacement, that was 0. Now I guess we'll use the right boundary. So when x equals L, for all time, this needs to be 0, because the right endpoint is fixed for a string. The right endpoint is fixed. Its vertical displacement is always 0. So, of course, this is changing with time. We don't want b to be 0, otherwise we get a trivial solution. So it's the same story, as should be very familiar right now. It's the sign that has to be 0 to satisfy the right boundary condition. Therefore, the argument of sine has to be an integer multiple of pi. Alright. So now we know what k is, correct? So let's update our function. We have b sine of kv times sine of k times x. Alright, and this is a solution for every integer n, so we'll just subscript this with an n and then get the total solution, general solution, by using superposition. Again, I'm going to go ahead and start the index at 1 because when n is 0 we get sines of 0, so it doesn't matter. Uh-oh. My bad, my bad. Right here, it's a function of time here. This was t. Okay, cool. Alright. Alright. Okay. So the last thing that we need to determine are these coefficients b sub n's, right? And so what would we use there to find that? Well, we use the left endpoint, use the initial condition for displacement, right? And we use the right endpoint. So now we're just left with the other initial condition, namely the initial condition for velocity. Let me copy this. The initial condition for velocity. Okay. Was right there. Okay. At time 0, the velocity was given by this piecewise function. Alright, so this means that when t is 0, oh crap. Okay, when t is 0, we're in trouble because we have a sine. Oh yeah, crap, they have a warning in the problem as well. Okay, so how can we deal with this? Oh, wait a minute. I'm so silly, right? This is the initial condition for velocity, and I'm panicking because I'm looking at position, not velocity. So we have to differentiate this first with respect to t, right? Initial velocity. So the derivative of y with respect to t. Oh, jeez. So you can just differentiate term by term here in the sum, and we're just differentiating with respect to t. So we're going to get that, right? Differentiating that sign. Alright, so derivative of sine is positive cosine, or plus cosine. So we have b sub n times L over n pi v cosine n pi v over L t. And this other sign was a function of x, so you leave it alone as we're just differentiating with respect to t. That's better. Alright. Alright, so now at time 0, there's nothing catastrophic happening, right? Cosine of 0 is 1. I'm gonna erase. I forgot to make this paint canvas large enough. I guess I could always change it. All right. Alright, so at time 0, right, we get v of x. So now we can find the coefficients b sub n the kind of standard way. Okay. All right. So what is the period of this? It's going to be, the principal period is 2L. So we're going to find the coefficients the same way as before, right? We're going to pretend that this v of x, this v of x is only good for the interval from 0 to L, right? But we can extend it so as to make v of x odd, and then we can take advantage of the Fourier coefficients for odd functions. So Bn is 2 over L, integral from 0 to L. And right, and what are we integrating? We're integrating n pi v over L times v of x. Yeah, I didn't really write that, but I should have brought this to the other side by dividing by it, right? Okay. Oops. And times sine, of course. And so that's just evil integration. It's a piecewise function. Can we take advantage of anything? I don't know about that. Well, we would just have to integrate. Parts. Alright, let's just integrate at least one piece, right? So, let's say we integrate from 0 to half of L, where our function v is 2h over L times x. And then we would have to do another integral. And I'm sure I could take advantage of some like symmetries or anti-symmetries or something. Oops. Unfortunately, it's two integrals because it's a piecewise function. This v of x. So we would have to evaluate both of these integrals. Alright. Let me check the stream, because I don't know, do you guys really want to see this? Yeah, music meth. This will automatically be archived. So, if you want to repeat. So, I really don't feel like integrating this. I know it's a cop out, but does anybody want to like maybe look at complex stuff? Any questions about residues or anything? Thanks, Thomas. Or I could just... Alright, residues, cool. Let's get some problems here. So let's look at some easier ones. Okay, clear the board here. Alright, so I'm going to, first of all, we're going to talk about residues, but we're also at the same time going to remind ourselves of the residue integral theorems, right? So if you do an integral over a contour, a closed contour, and you have a function, okay, this is equal to 2 pi I times the sum of all residues of f inside the contour. Okay. So for example, so here's your generic contour. Your function is analytic, except at some singularities, and some of these singularities could be inside. So we would have to find the residues of the function inside, and that integral of the function would be 2 pi I times the sum of all the residues here. Okay. All right, so here's an example. Suppose you want to integrate e to the minus z over z cubed dz. And suppose you're integrating over this circle. All right. Okay. So what I would do is I would look at two things, right? I would look at the function you're integrating and figure out, and I'll do number 7, sure. Let me just finish this. Figure out where the singularities are. Well, the singularities of our function here are at 0, right? I mean, there's only one place where the denominator is 0. Okay, so then we check, or you can even draw the region or the path we're integrating over. Here we're integrating over a nice circle centered at z equals 2. And what's the radius of the circle? It is 1, right? This is the form of a circle and using complex numbers. Z minus center, magnitude of that must be the radius. So the radius is 1. That's our contour. And where is our singularity? Well, our singularity is here. So the residue theorem for the integrals tells me that this is 2 pi I times the sum of the residues of the function inside. Well, that would be 0. There are no residues, right? So this integral is 0. In general, if you have a function which is completely has no singularities on the contour or inside the contour, right, that you're integrating over, then the integral must be 0 because there are no singularities and residues inside, or residue is 0. Right, so that would be different, of course, if we would integrate the same function but over a different circle. And this is probably maybe a little easy, so times, well, let's see whatever the residues are, right? Alright, so this time, or this is the complex plane, so okay, this time we have a circle of radius 2 rather, centered at the origin, and our singularity is the origin. Therefore, we do have a singularity inside. We can find the residue. So for this easy problem, I would probably recommend Lorentz series, right? And it's simple because we know the series expansion for e to the minus z. It's the sum as n goes to from 0 to infinity of the exponent That's minus z to the power n divided by n factorial. That's just a standard expansion for the exponential function. We can even write out a few of these terms. Okay, when n is 0, when n is 1, when n is 2, when n is 3, when n is 4, 4 factorial, yeah, 24. When n is 5, and so on. 5 factorial is 120. Okay. And then I would go ahead and distribute the 1 over z cubed factor. Okay. Right, so plus, all right, and so on and so forth. Okay, so you recognize this as like the Laurent part, right, where we have powers of z minus the center in the denominator, and this is like the Taylor part. You have your constant, and you have your powers of z. And let's recall that in the Laurent series, see, the center is a. That's a cubed, that's a squared. It's this b1 coefficient that's important, right? It gives us residues. Oops, I didn't mean to do that. And so on. But anyway, what's important is this b1. It gives me the sum of the residues in the angular region for which we did the Laurent series, right? So here we the Laurent series is for the region. We only have one singularity, so it's for everything except the origin. Yeah. That's for all, the whole plane except the origin. So the b1 would be the residue of the sum of the residues of the function inside, of the singularities inside. So this this 1/3 is our b1. Right, it's the coefficient for 1 over z. That must be the residue. Okay, b1 is 1/3. So we get 2 pi I, and then the residue is 1/3. So that's our integral. Okay. Another way to have found the residue is that I don't know if you see that this is a pole of order 3, right? Because it's this factor which makes the denominator 0 at 0 has multiplicity 3. So there is a formula for that residue. Then the residue of f at 0 would be, okay, so what you do is, what's the formula? You take z minus a to the power m, where m is the order of the pole or a greater integer, and you multiply the function. So this is just formula for a residue of the function at a. And you differentiate this m minus 1 times. Right. And then I believe you evaluate at a and divide by m minus n factorial. I forget it. I think you have to divide by a factorial. Chapter 14. 14. Just really quickly, I'm sorry. I mean, yeah, divide by m minus 1 factorial. I mean, I could have derived that, but, you know. Thank you. Alright, and then evaluate this at z equals a. Right, so I could have found the residue that way. But that you would have to have known ahead of time that this has, you know, this pole has order 3. So right, we'll differentiate m is 3, so we'll multiply by z cubed, i.e. we'll get rid of the denominator. We'll multiply our function. All right. Let's see. Is that even on screen? 1 second. I don't think so. There you go. Sorry. All right. Our function is e to the minus z divided by z cubed. Okay, and then we'll differentiate this twice with respect to z. Divide the result by 2 factorial and evaluate at z equals 0. So that's pretty simple, right? We just differentiated e to the minus z twice. So once, twice, you get this. Divide by 2 factorial at z equals 0. It gives me 1/2. Yeah, so that was, whoa, 1/2? Yo, something's wrong. How did I get... I'm confused. Oh my lord. Okay, when n is 2, 2 factorial is 2, not 3. Alright. My bad. This is 2. So b1 is 2. I mean, b1 is 1/2. So this is 1/2. So I get pi I. Man, I'm sorry about that. Go figure. 2 factorial equals 3 all of a sudden when it's, well, it's noon already, but... Alright. But it matches, right? Okay. And that was easy, because we knew the expansion for e to the minus z. The harder ones are where you have this rational function where you have to use geometric sum. So let me go ahead and check what number 7 from section 4 is. Number 7 from section 4. Oh, sure, that's good. Okay. All right, number 7. So this is chapter 14, section 4. Problem 7. All right. So number 7 says they give us this rational function. Now it's not analytic everywhere, right? I mean, we have a denominator, and this denominator is 0 at z equals plus or minus 1. Okay, so those are singularities. Now, here we can kind of not cheat, but we can find the residue quite easily without Lorentz series, just to confirm whether you're right about what the residue is or isn't, by noticing that the denominator can be factored. It's a difference of 2 squares. And then we see that each singularity at both z equals 1 and z equals -1, both are poles of order 1. These are simple poles. I should have a self-deprecating joke there. Simple poles. All right. Right, so if I wanted to find the residue of the function, say at 1. So residue of my function at z equals 1. I could just multiply my function by 1 minus z. Right, because m is 1 in our formula that we wrote. And then differentiate 0 times and divide by 0 factorial, right? Evaluating at z equals 1. So these cancel. So at z equals 1, we get 1 over 2. So the residue at 1 should be a half. Now the residue of the function at negative 1 again, we're going to multiply by the factor 1 minus the negative z. So 1 plus z, we multiply our function. At negative 1. Cancel, cancel. So we get 3 over 2. Well, the residue at the origin is 0, as you said. So let's see why, I guess. So let's do a Laurent series centered at the origin, right? I mean, clearly there's no singularity at the origin, so the residue would be 0. But okay. But this is good practice for Laurent series. So, all right. So the first thing we're going to do, if we want to find a well, let's just think of there's 2 issues. The center, right? Center is 0, the center of expansion, and then there's the region for which we want to find the Laurent series. Okay. So I can center, so if I center my Laurent series at the origin, I'll have 2 regions, right? I can find the Laurent series for the angular region up to the first singularity. So starting at 0, when you go out, you get a disk of radius 1 until you reach your first singularity at 1 or negative 1. Doesn't matter which one. So the first region is, let's call that region 1. Region 1 is described by the inequality, right? This is region 1 consists of all the complex numbers whose distance from the origin is greater than 0 because, well, wouldn't matter. Less than 1. And of course there's a region that's outside this unit disk, region 2. So that'd be described by the inequality where the magnitude of my z's in region 2 is greater than 1. All right. So I would expand, say, I would do a Laurent series for region 1 first, right? You're going to get 0, I mean, for the residue, clearly. All right, so, but the process by which you do this, of course, is important. So we first use partial fractions. Yeah. No, I wouldn't. Okay. Oftentimes you would use partial fractions, right? You factor the denominator, and then oops, that was silly. And then you see after you factor that you have 2 linear factors, multiplicity 1. So you can write this as some constant over the first factor plus some constant over the second factor. Okay. And then you can figure out what A and B are. You just multiply both sides of this equation by the common denominator. 1 minus z, 1 plus z. And then you can solve for A and B. So we're looking for coefficients A and B that work for all z's. So that'll work for particular values of z as well. So for example, z could be 1. In which case the left-hand side is 1. The right-hand side was 2a. And I chose z equals 1 because of course it makes this factor 0. So a is a half. And likewise, I could, similarly, I can say let z equal -1. So the right-hand side becomes 3. The left-hand side becomes 3. The right-hand side becomes 2b. So b is 2/3. Suspicious, isn't it? All right. Right, so once you have that partial fraction decomposition, let's see, a minus z, a is a positive 1, plus b. Right, so you could do this and then you use expansion on these. Geometric expansion. We'll do that, but here I just want to observe that the original function, the denominator is already of the form that we'd like. So let me just work with that first. All right. All right, so what I'm saying here is that if I factor this into the numerator times 1 over the denominator, right, is this factor not already in the form of 1 over 1 minus r, right, which we know can be expanded geometrically into the sum and goes from 0 to infinity r to the n, as long, of course, as r has magnitude less than 1. So in this factor right over here is exactly of that form. And notice that since region 1 we have magnitude of z is less than 1, the magnitude of z squared, if you square both sides, is 1 as well. It's magnitude less than 1. So that can be directly expanded into z squared to the power n. Right. Perfect. Okay. So then we can finish this off. So now this is 2 minus z times the series expansion for that second factor. Right, and then you can multiply through, I guess. You'll get really 2 sums. But the point is that none of the powers here are going to be negative, right, for the z. So we won't have like a b1 or something. Yeah. So if I expand this, let me combine these, I guess. Well, notice what this is. Yeah, this is like has the even powers, and this has like the odd powers. So, like if you start at 0, so you get 2 minus z plus 2z squared minus z cubed, and so on. If you want to write out some terms. But notice that we don't have any z's in the denominator. In particular, we don't have b1 over z, right? So this means that b1 has to be 0. So residue is 0. Yeah. So you're right on. Now, what would but for practice, you should be able to do the Laurent series for region 2 and be able to understand what B1 represents there if it's non-zero, right? So for the second region, we get this. The second region is defined by that inequality. Oops. We're simply looking at all points outside that unit disk. We want to find the Laurent series for that region centered at 0. So there we would have to use the fact that 1 over z, magnitude of z, is less than 1. And even better, if you square both sides, you get 1 over magnitude of z squared is less than 1. Alright. Because then we can look at our function. And I'm not using partial fractions because this is already in a convenient form. And then, right, if I want to use geometric expansion for that second factor, of course r has to have magnitude less than 1. But z squared over here has magnitude more than 1, right? Because we're in this other region, we're outside the unit disk. So we want to take advantage of this fact that if you divide both sides by the magnitude of z squared, you're going to get something less than 1. So if you factor out a negative z squared, just write that over here, what you'd be left with is, crap, I'm getting ahead of myself. See, factor out a negative z squared, you get 1 minus 1 over z squared. So why is that good? Well, because then we have something in the form 1 over 1 minus r, this thing I'm talking about, where r is 1 over z squared, and we see the magnitude of r in the second region we noted was less than 1. So you can expand this factor geometrically. And you get r to the power n looks like this. Alright, and if you don't, I can just, I'll go ahead and write out a few terms. So when n is 0, when n is 1, when n is 2, and so on. Now I'll distribute the this factor into the parentheses. And then the FOIL, so to speak, right? So distribute this factor. So 2 times all that jazz. And then minus z times all that jazz. So You get plus 1 over z. So it looks like we got the, yeah, great, and so on. So let's see. So if you line this up correctly, right, we're looking for this term, constant over z. There it is, constant over z. So that's 1. b1 equals 1. Right? But what does that mean? What were the residues? Did I do that right? Fudge. Fudge, fudge, fudge. Okay. That should give me the sum of the residues at 1 and -1. That should be a 2 somehow, somewhere. Oh, brother. Yeah. Well, I think I'm just going to end it there. This is too long for me now. Let's see if I did this right. Z is 1. It's a half. Z is -1. Yeah, I don't know what's going on. I should be getting it too. But anyway, gosh, I don't know who's watching, if anybody's watching, but I'm out of here. This will be up. Or better yet, just come to the math lab. Doing this over YouTube is a lot more difficult than I thought, but it's fun. Alright. Thank you for watching. I appreciate it. I'll see you in the math lab, alright? Thanks, Thomas. Bye.